start my video and then I'll try to start. Can you see my screen there?
Yeah, we can see it.
What do you see? I have several screens, so I just want to make sure that.
I see the slides for the character tables for a point group.
Okay. Do you see anything else except that? Do you see?
I just see that.
You see me too?
I see you too.
That's good. That's wonderful. So I can go over the presentation. So today we're talking about character tables and the point groups. And once we understand what a character table, we will try to use these character tables in predicting what type of orbitals of an atom would be involved in either hybridization or the formation of molecular orbitals. So the way we do this is a character table, as you can see here. It is just a table. Can you see my pointer here?
Yeah.
Okay, excellent. Okay. So what we have in all character tables is on the left-hand side top column, you have the point group label. For example, if this were to be a C2B point group, remember those of you who have done point groups, I think I uploaded a refresher course on point groups. So that should be good for you, at least for those of you who did not have a good understanding of the point groups. That would be a good starting point. So, for example, if you have water molecule, you will have a point group of C2B. So, this is the point group label. So, all tables will have the point group label situated in the left-hand side top column, at the top entry. And then in the red, you have letters such as E. E refers to identity, that is doing nothing. All right. C2 is basically rotating the molecule by 180 degrees. That is 360 divided by 2. And then you have two vertical planes of symmetry. One is XZ plane and the other one is YZ plane. All right. Now, in all these coordinate system, the Z-axis refers to the molecular axis or interatomic axis. Okay, that's something that you have to keep in mind. All right. And then in this particular example, I have one identity, one C2, one sigma V, and one sigma V prime. So altogether, I have four different symmetry operations. That is what is known as the order. So when we say C2V has an order of 4, that means there are 4 unique symmetry operations that are present in this particular point group. This is clear. So we will go over several other character tables too, but I'm just giving you the definition. So whatever character table you look at, these are the terms that you'll be seeing. And then in purple, we have this A1, A2, B1, B2. These are called symmetry representation labels. A and B refer to what we call singly degenerate. That means there will be only one possible value for the character. Okay? Now, when we have A and B, the difference is a symmetry representation is labeled A if it is symmetric with respect to a C2. For example, if you look at the entries for C2, for both A1 and A2, we have +1. That means it is symmetric with respect to the principal axis of rotation. If you look at B1 and B2, they have -1. So that is the difference between A representations and B representations. But both are singly degenerate levels. That means these operations are only single, not multiple. Now, finally, we have a character that is designated as 1 or -1. 1 means it is symmetric, nothing happens to it. -1 means it changes. So that is the difference between the characters. So in this character table, the entire matrix that you see +1s and -1s, that means either that is symmetric or anti-symmetric. Finally, the yellow column, that yellow row that you see, 1, -1, -1, 1, that entire row is called a representation. So this 1, -1, -1, 1 corresponds to the representation of B2. Similarly, for A1, it is 1, 1, 1, 1. For B1, the symmetric representation is 1, -1, 1, -1. One of the important aspects of this is all these symmetry representations are orthogonal to each other, which means, for example, let's say A1 and A2. All right, so pay attention here. For the E, it is 1 and 1. So 1 times 1 is 1. For C2, 1 times 1 is 1. But sigma V, it is -1, and sigma V prime is also -1. So when you add all of them, it is 0. You see that you can also try that for A2 and B1. So for example, 1 times 1, 1 times -1, -1 times 1, and -1 times -1. If you add all those numbers, again, it becomes 0. So when it becomes 0, we say they are orthogonal. So all 4 symmetry representation labels in the C2V point group are orthogonal to each other. That is a very important condition, right? Any questions up to this point? We are going to move with lots of examples to understand much more in detail. Are there any questions? A copy of this is also in your Canvas folder, so you don't have to write down. So the next one is, in addition to these character numbers, we also have what we call symmetry functions. A z, x squared, y squared, z squared. We'll get into all these definitions very quickly. R means rotation. When they say R sub z, it is telling you the rotation along the z-axis. Similarly, if you have 2 of them, x, y together, that is the xy plane. Similarly, y, z, zx. In addition, we also have x, y, and z separately. Okay? So these are all, again, one way to look at them is, if I'm talking about z here, you can imagine you're talking about a pz orbital. Similarly, if you're talking about x here, you're talking about a px orbital. It is a dumbbell oriented along the x-axis. Similarly, a y is again a p orbital, like a dumbbell, oriented along the y-axis. Similarly, if you look at xy, yz, and xz, these are all the d orbitals. You all must have seen the shapes of the d orbitals, right, in the inorganic chemistry class. You have a double dumbbell, which is what a d orbital looks like. If the double dumbbell is placed in between the x and y axis, then we say it's a dxy orbital. If that double dumbbell is located between the x and z axis, we call that dxz. Similarly, a yz means that double dumbbell is located in between the y and z axis. On the other hand, you can also have orbitals located along the axis. For example, you have dx squared minus y squared, which is the double dumbbell oriented along the x and y axis, not in between, but along them. Similarly, a dz squared orbital is the d orbital that is oriented along the z axis. So, quick notes here. When we talk about A, we already said it is symmetric with regard to the rotation about the principal axis. So principal axis of rotation is C. If the value is symmetric with respect to the principal axis of rotation, then we will give the value A. And if it is anti-symmetric, we give B. So that is the difference between A and B. For example, in the exam, I give you a representative character table, and I fill in the A's and ask you to predict what should be the B here. So your answer should be, if A is symmetric, then B should be anti-symmetric, so it should be -1. This is how you can predict the character values. The subscript numbers are used to differentiate symmetry labels when necessary. Okay, so a 1 in the character indicates that the operation leaves the function unchanged. So which means it's called symmetric. If it is -1, that indicates the operation reverses the function. It's called anti-symmetric. Am I clear here of all the terms? So we have the point group, symmetry operations, E, C2, sigma, sigma, V prime, and symmetry representation labels, A1, A2, B1, B2, and then we have the characters, and we have also symmetry functions here. Any questions up to this point before I continue to the next slide? Well, it's okay, right? We are just looking at the definitions and the language of a character table. Let's now move on to the next slide. Let's now look at a PZ orbital, which is shown here on the left-hand side, with wave function positive on the top and wave function negative, right, on the bottom. So we call that like an arrow here pointing in this direction. So the wave function is negative when it is white. Let's say it's positive when it is grayish or flipped. Now, a PZ orbital has the same symmetry as an arrow pointing along the z-axis. So if you now write the Cartesian system, x, y, and z-axis, your arrow or your p orbital is located in this fashion. So now I'm going to apply all 4 symmetry operations on this arrow to see what happens to this arrow. Right? There are only 2 possibilities. One possibility is that arrow stays exactly the way it is, or it changes its direction. So if it stays the same, the character value is 1. If it changes the direction, the character value will be -1. So there are 4 different symmetry operations here, E, C2, sigma V, and sigma V prime. Now, E is doing nothing. If we don't do anything, this arrow remains exactly the same. That's the reason why the value is 1 here. All right. If I do C2, remember z-axis is your highest full rotational axis of symmetry. So if you rotate this arrow along the z-axis, it again remains unchanged. So the value is going to be +1. Similarly, if you were to reflect this arrow either in the xz plane, xz plane is this plane here, you can see the z-axis and the x-axis, or yz plane, which is this plane and this. That's the plane of your paper if you like. Okay, and if you do those reflection operations, again, you will find that the arrow remains exactly the same. So under all 4 symmetry operations, the character value is 1. So if you now go back to your character table, you find the symmetry representation label, which has all the 4 ones. So E is 1, C2 is 1, sigma V is 1, sigma V prime is 1. So this must be your A1 symmetry representation. So in A1, as you can see, we have Z. That's the reason why a Z orbital is placed here. Or even if you have dx squared minus y squared or dz squared orbitals, the result will be the same. We will see that as we go through more and more examples. So that is how we say the Z belongs to the A1 representation in the character table of C2b. Is this clear to you? Does that make sense? Let's go through several examples. Let's now pick up px orbital. That is, now I have a lobe just like the z orbital, but this time this dumbbell is oriented along the x-axis with the positive wave function on the top and the negative wave function on the back. Okay, so you can imagine this is the plane of the screen is yz and x is coming out of the screen. All right. Now, when I do nothing, always the value will be 1. That's why when you see the E entry, all character values for the E are +1. That is because nothing changes. You're doing nothing. You're not doing anything. Similarly, if you were to reflect this arrow in the XZ plane, that is this and that plane, this arrow again remains the same. However, note this. When you do a C2 on this, that is, rotate this arrow along the z-axis, suddenly the arrow will change its direction from this to that. So that means there will be a flip of 180 degrees, which means it is now antisymmetric. So we have a -1 for this. Similarly, if you were to reflect this in the YZ plane, that is the plane of the screen itself that you're looking at, then if you reflect, the reflection will look something like this because it gets flipped. So in both cases, it will be -1. So now if you look at which symmetry representation has 1 for E, -1 for C2, +1 for XZ, and -1 for YZ, suddenly you find you have the B1 symmetry representation label. So the B1, that's the reason why you have a value of X here. The X means PX orbital. Okay. Similarly, you will get the same result if you were to do the operations on the DXZ orbital. That also will give you in the C2V representation. Okay, will be B1. Questions? Are we okay so far?
I have a question. Why are we rotating around? Why are we reflecting according to the z-axis?
Which axis you're talking about? Z-axis is the generally it is parallel to the highest pole rotation axis of symmetry. So that's your C2 axis. Right there.
Oh, okay, that's why. Got it.
By default, Z is given the highest priority in terms of orbital. So that's how we orbitally choose. Does that make sense, Vivek?
Yes, thank you.
So when you're doing C2, it's not X or Y, it is always along the Z. Good. So let's now look at another orbital. This time I'm looking at the PY orbital. The PY now has an arrow along the y-axis. And if I do nothing, which is E, that's going to be +1. And if I were to reflect this in the YZ plane, the YZ plane is basically the plane of the screen itself. So if you reflect in the YZ plane, the arrow still remains the same. So under these two conditions, it will be +1. However, if you do a C2, just like the previous example, right? If you were to rotate this along the Z-axis, this arrow will turn 180 degrees, flip it to the other side. So this is the resulting configuration we have. So we can say under C2 and XZ plane. XZ plane is the plane perpendicular to the screen here. So if you were to reflect that arrow perpendicular to the plane, that arrow will change its position from left to right to left. So it flips. So now I have a condition where it is +1 for E, +1 for sigma V prime. However, it is -1 for C2 and -1 for XZ. So if I now look at these values, I find it corresponds to a B2 representation. Because in B2, E is 1, C2 is -1, sigma V is -1, and sigma V prime is +1. That is the reason why the Y orbital in the C2V point group is given the B2 representation. Does it make sense? So we have now seen PZ orbital, PX orbital, and the PY orbital. Just by looking at the orientation of the orbitals, looking at the Cartesian system, looking at the symmetry operations this molecule has, and knowing that this is C2V, you have these representations. So this is how the values are derived. For you guys, you're lucky because you don't have to memorize all this, because in the exam, you're allowed to look at these character tables that are available pretty much, if you Google the word character table, there are several character tables that you find. So you don't have to memorize. However, you need to understand what these terms really mean. What does a 1 mean? What does a -1 mean? What does X, Y, or Z mean? What is the meaning of A1? What's the order of this group? What are symmetry functions? Okay, because we will be using this knowledge to identify the orbitals that combine to form the hybridization models. Questions? Hearing none, we'll move to the next slide where we briefly talk about rotations. Although rotations are not important as far as this course is concerned, but it is still something that you may want to keep in mind. So let's say now if you can see the Cartesian system, my XY is in the plane and the Z-axis is perpendicular to the screen. Okay? So now if I have an object that looks like this, if you do nothing, again, the sense of rotation does not change. And if we were to do a C2 operation, which is now z-axis coming out of the screen here, and if you rotate anti-clockwise, again, no change. So E and C2 are +1s. However, if you were to reflect either in the XZ plane or YZ plane, you can see a change in the sense of rotation. So for example, right now we have anti-clockwise, and when you were to reflect this image on either XZ plane or YZ plane, it suddenly becomes clockwise. So that change in the sense of rotation gives you antisymmetric values. So if you now look at all these values, you get 1 and 1 for E and C2, -1 and -1 for YZ and XZ planes. So that is the reason why the Aussie symmetry function is located corresponding to a symmetry representation of A2. Is this making sense now? So similarly, if you have a dxy orbital, this is something that I want you to try once the class is over. You can draw the dxy orbital and do the operations, and you will find that the symmetry values will be 1, 1, -1, -1. All right. Are we okay so far? We'll also look at the d orbital still to see how the symmetry changes. All right, so let's now look at the d orbital. So what do you think this orbital is? This is an orbital in the plane of x and y with positive function and a negative wave function, and they are located in between the axes x and y. So this orbital should be labeled as dxy. Now, the z-axis in this case is normal to the viewing screen. The screen that you're looking at, the z-axis is perpendicular to the screen. Right. So when you do E, that is do nothing, it does not change the wave function orientation. If you look at the C2, C2 is rotating this along an axis perpendicular to this plane by 180 degrees. When you do that, this lobe will come here, that lobe will come back, this will go there, and this will come here. So the resulting structure is indistinguishable from the original one. So it appears nothing has changed. And for that reason, the E and C2s are +1. On the other hand, if you were to do any reflection in the XZ plane, so the way you look at the XZ plane is that it's a plane that contains x-axis and the y-axis, which is pointing towards you. When you do that, then what happens is this one gets reflected there, this comes back here, and the resulting structure looks like something has changed here, the wave functions. So that's -1. So now again, by looking at 1, 1, -1, -1, you know that xy is is the one that corresponds to the A2 symmetry representation. Am I making sense here? Questions up to this point? If I'm going too fast, you got to press the brakes on me. All right, let's move on.
Professor,
Yes.
could you speak closer to the mic, because sometimes it's very hard to hear you.
Can you hear me now? Because
Yes.
somehow I'm speaking to the computer, and I don't know if there is a control here. But is this okay now?
Yeah, if you are closer to the mic, it's better.
Okay, all right. I don't know where the mic is, but I'll come as close as possible to the computer and talk about it, okay? Thank you for letting me know. So let's move on to the next one here. This is, what orbital is this? The top one is your dz square orbital. The dz square looks like this. The lobe has this positive wave function, and there is a halo right there that has a negative wave function. Or you can also look at xy, x squared minus y squared. So if you look at both of the orbitals along the z-axis, the dz squared looks like the one that is given on the top, and the dx squared minus y squared looks like the one in the bottom. Now, if you do E, C2, sigma xz or sigma yz, no matter what you do, in all 4 operations, the shape or the orientation of the lobes in this orbital remain unchanged. So this now belongs to A1 symmetry representation, because only under A1 in the C2V group, you have 1, 1, 1, 1. So instead of saying dx squared minus y squared and dz squared, the way the functions are written is anything that is x squared, y squared, and z squared. Any combination of those will correspond to the A1 symmetry representation. Does that make sense? So we're going through each and every orbital and then applying it to just one point group, that is the C2E. I'm not changing that. But you should be able to do that for other point groups too, as long as you know what the character tables are. So we're going to go that with that road too. So here is an example of two different point groups and the character tables. All right, so on the top, we have the point, the character table for C2V. In the bottom, we have for D3H. So C2V, you can imagine it is for water, and D3H is the one that I showed you in the previous lecture, BCl3, right? BCl3 is a D3H point group. Now, if you look at these two, there are certain things that we have to be careful about. When I say x squared, y squared, and z squared belongs to A1 representation, that is true only if the point group is C2V. On the other hand, if you come to D3H, that x squared, y squared, and z squared, as well as x squared minus y squared and dxy orbitals, now belong to a different representations, A1 prime and E prime. Okay. So when you change the point group from C2V to some other group, your symmetry functions also change their place. So that is something, that's the reason why I put a blue arrow here, just to pay attention here. So now that we have a D3H point group, what should be the order of this point group? We said in C2V it is 4, right? Because 1 plus 1 plus 1 plus 1, 4. On the same account, what should be the order in the D3H?
Six.
That's 6. Let's count it again. I have 1 E, right? I have 2 C3s. So 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 1, 7. 7 plus 2, 9. 9 plus 3, 12. So the order of D3H point group is 12. That is something that you have to keep in mind, because if you have a C3, right? A C3 can be rotated 2 times, C31 and C32. C33 is again identity. So we only count 2 C3s. Similarly, because it's a D3H group, normal to C3, there are 3 C2s. Remember, the C3 and 3 C2s give you this D group here. So we have 3 C2s, and there is a horizontal plane of symmetry. As you all recall, horizontal plane of symmetry is the plane that is perpendicular to the highest 4 rotational axis of symmetry. So for D3H, the highest 4 rotational axis of symmetry is C3, and you have a plane that is normal to the C3, that's the plane of the molecule itself, that should be called as sigma H. And then you have 2 S3s. So S3 is rotation by C3 followed by a reflection in the plane perpendicular to it. We have 2 of them here, just like we have 2 C3s, we also have 2 S3s. And then there are 3 sigma Vs. The sigma Vs will be perpendicular to the molecule and contain at least one of the bonds in the trigonal planar molecule. So altogether, we have 12, that is the order. In addition, we also have A1s, A2s, and E1s, okay? Now let's look at this thing a little bit here. What do we say about A? The characteristic of A is, if you have the highest 4 rotational axis of symmetry, for all A symmetry representations, that character should be 1. which is true. If you look at A1 prime, it is 1, A2 prime, it is 1, A1 double prime, it is 1, A2 double prime, it is also 1. Okay. Now, the second thing is, what is the difference between A1 prime and A1 double prime? Focus your attention on the sigma h. So if it is symmetric with respect to sigma h, then it is called single prime. If it is anti-symmetric with respect to sigma h, it's given double primes. So that is the determining factor between single primes and double primes in the symmetry representation tables. Am I making sense here? Similarly, if you look at E prime and E double prime, in the E prime, sigma h is +2, and E double prime, sigma h is -2. So it is the sigma h that determines whether you have a single prime or a double prime. Okay. We also learned that A are singly degenerate levels, but when you talk about E, it's a doubly degenerate level. It means there are two things that happen simultaneously. That is the reason why when you look at the symmetry functions here, for E prime, you have X and Y coupled together in a parenthesis. You don't see that for A or B's because A and B are freely given as single functions. Similarly, if you look at E prime here, X squared minus Y squared and XY, they act like pairs. So in other words, this is a doubly degenerate level. If you have three of them, then it is called triply degenerate, and we have a letter called T. So in all character tables, you get symmetry representational labels as A's, B's, E's, and T's. So I gave you now the definition of all of them, and we also talked about the differences between prime and double primes. Okay, any questions so far? You also must have noticed, some of you with a very keen eye, you must have noticed while the singly degenerate functions have an order of 1, but when you go to doubly degenerate systems, you have a value of 2 here because there are two things that we are taken together, combined. So similarly, if you want to have a T, there will be 3 values. Okay. So A's and B's will have single values, E's will have 2, and T, which is triply degenerate levels, will have 3. Am I making sense here? Questions? Let's go to the next slide. So if you now look at the D3, remember we just talked about E indicates that the representation is doubly degenerate. This means that the functions are grouped in parentheses must be treated as a pair and cannot be separated or considered individually. Whatever you do to X, you have to do to the Y also. Here is a great example. Let's start with 2 arrows, an object that has 2-dimensional signature, one along X and one along Y. Now, if I were to rotate that along C3, so what is C3 rotation? How many degrees you need to rotate? You need to rotate it by 360 divided by 3, which is 120 degrees. So when you do a 120 degrees rotation, so you have to go up 90 here and another 30 there. So that angle there is going to be 30, and that is 90. So 90 plus 30 is 120. Similarly, when you were to rotate this, this also goes down. Now, if you look at the cosine of 120 and the sine of 120 is 0.87 and negative 0.5. So when you look at all the changes here, so plus 0.87, minus 0.87, minus 0.5, plus minus 0.5, it gives you -1. So the C3 operation, E has a -1. Did you see that in the character table? That is where that value comes from, -1. On the other hand, if you were to do a C2, that is rotating this thing Of course, you're not separating them. You're doing a combined rotation of both the arrows along the z-axis. Now, in this example, the z-axis is perpendicular to the screen, and you rotate it by 180 degrees. So when you do that, the blue one will flip the direction, the red one will retain it. So the blue changes to -1, the red one does not change. So if you now look at the total change, +1 plus -1 is 0. That's the reason why for a E, C2 is 0. See that one, the value of 0 there. So I'm now giving you a reason why the characters are different for different symmetry representations. Are we making sense here? I mean, first time, it may be new to you because the language I'm using, you may not have heard before, but that's the reason why I'm going extremely slowly, looking at each and every. I'm doing a basically an anatomy of a character table, looking at each value and trying to explain to you what these things really mean. Are we okay so far? Of course, this lecture will be uploaded and you will have plenty of time to review that at your own pace. Moving on, this is the symmetry representation for an octahedral group. See how big that table is. You can't have any character table more complex than this. An octahedral. So what's the order of this character table? That's the type of questions we get in exams. So let's throw the character table and so on. I mean, GRE is true, that's what they say. Do you know anything about character tables? OH means octahedral. Octahedra is one of the most symmetric objects that we know. It's one of those platonic solids, if you heard of the word. The cubes and the octahedrons are some of the most symmetric ones that are seen in nature. So what they have is they have identity. All of them will have identity. And they will have 8 different C3s, 6 C2s, there are 6 C4s, 3 C2s, and an inversion center, I, 6 S4s. When you will have 6 C4s, you will have 6 S4s, and you will have 8 S6 molecules, and then 3 sigma H values, and 6 sigma Ds. That is the dihedral plane of reflection. So look at the entire cascade of symmetry. So this, you can't have a character table more complex than this. So if you now look at the order of this, is 1 plus 8, 9, 9 plus 6, 15, 21, 24, 25, 31, 39, 42, plus 6, 48. So the order of this character table is 48. That's huge. And then you have couple of other things that you can see. We have A1s, right? So A1, G, and A2Gs. Okay. So if you look at G and U, we talked about that in the previous inorganic chemistry class. What did we say about G and U's? G refers to G is an abbreviation for a word, right? What is that word? Anyone can open your microphones.
Gerade.
Gerade, you're absolutely right. And you?
Angarade.
Ungarade. Gerade, Ungarade. That is, now if you look at Gerade and Ungarade, that is with respect to the point of inversion. Now I want you to pay attention for T1G and T1U. For T1G, the I value is +3. For T1U, the I value is -3. So that's symmetric with respect to point of symmetry, point of inversion, and anti-symmetric with respect to point of inversion. So you have 2 choices, Gerade and Ungarade. So that's where the plus and minus. So these are all the small things that you have to pay attention to. Similarly, A1U and A1G. If you look at A1G, the I is +1. If you look at A1U, the I is -1. So the Gerade and Ungarade, they come when you have an object that has a center of inversion. or point of inversion. So these are all different examples. E again represents doubly degenerate. A represents singly degenerate. The T here represents triply degenerate. Now, if you look at the functions here, right, in T1G, you have Rx, Ry, Rz, rotation along X, Y, and Z combined together. So you're not doing one after other, but you're doing all of them at the same time. Similarly, if you look at T2G, we have XZ, YZ, and XY. This is very important because we will be talking about the set of the d orbitals as being T2G orbitals as we go through the coordination complexes. But it's nice to see that in the character table coming up and showing this. So now we have octahedral symmetries. We have C3s, C2s, C4s, and sigma H. So what is the difference between sigma H, folks? What does sigma H do? Remember, if you have a prime and a double prime, that is when the sigma H becomes important. But here we don't have anything with a prime and double prime, so we don't have to worry about the effect of sigma H. In this character table, the most prominent thing is your center of inversion. That is the one that distinguishes between Gurade and Ungarades. Okay. So basically that's summarized here at the bottom. T indicates that the representation is triply degenerate. This means that the functions grouped in parentheses must be treated as a threesome and cannot be considered individually or separately. So this is, and subscripts Gurade, Ungarade, the symmetry representation level indicates symmetric or anti-symmetric with respect to the inversion center. In fact, for those of you who did my class in the symmetries, we did talk about this Gurade, Ungarade, how the wave functions change across the point of inversion. All right, any questions? So you have seen one of the simplest point groups, such as C2E, and one of the most complex character table, that is your octahedral. It's one of the platonic solids, octahedral, tetrahedrals, cubes. These have, because they're highly symmetric, and for that reason, there are lots of symmetry operations that are possible in these geometries. All right. Now that we understand the language, we're going to start working, come back to our chemistry, and then see how a character table can be used to describe the atomic orbitals in a molecule. Okay. The first thing, if you're given any molecule, the first thing that you need to do is draw the Lewis structure, know the symmetry elements, use the point group chart, and determine the point group of the molecule. Right? If it is H2O, then you know the point group is C2V. If it is CH4, the point group is tetrahedral. If it is BF3, the point group is D3H. If it is PCl5, it's again D3H. Right? So once you draw the Lewis structure and then apply the Vesper theory, you know the geometry. Once you know the geometry, you can find the point group. Then the thing is, you need to now keep a character table corresponding to that point group on your left-hand side. And then what you need to do is, you need to do what is called a reducible representation tau for the type of bonding you wish to describe. So the molecule may have just only sigma bonds, it may have sigma and pi bonds, or it may have just few sigmas and just, you know, 1 or 2 pi bonds, and it can have a pi bond in plane pi bond, or a pi bond that is normal to the plane of the molecule, which are given here, pi perpendicular and pi parallel. Right? So these are all the different symmetries that we need to consider. Of course, I will walk over all these cases separately, with each one giving an example. So we need to develop what we call a reducible representation, which tells you how the bonds are affected by symmetry elements present in the group. For example, if I rotate this molecule, how many bonds get displaced, how many bonds stay in in the same place. So these are all the things that we have to first consider and come up with what we call reducible representation. Once you have reducible representation, we need to convert the reducible representation to what we call irreducible representation using the character table. That gives you what symmetry representations are involved in the irreducible representation. For example, an irreducible representation looks like 2a1 plus b1 plus b2. That is your irreducible representation. All right. And once you know the irreducible representation, you can go back to the character table and look what orbitals are possible in A1, what orbitals are possible in B1, what orbitals are possible in B2, and come back and construct a sensible hybridization picture based on this. Right? So this is what we will be doing for all the examples that we will be taking care of. Right now, it may not mean anything to you unless we put this in action and try to demonstrate each and every one of these things. So let's now start our journey with a molecule called CH2Cl2. Okay. Dichloromethane, you all know this simple molecule. So if you want to look at the picture, this is how a dichloromethane molecule looks like. Okay. 2 hydrogens. I'm holding one of the hydrogens in my left hand, and then there are 2 chlorines, which are like blue spheres. 2 hydrogens, 2 chlorines. That's a tetrahedral-like molecule. But is this really a tetrahedra? It looks like a tetrahedra, but does it have all symmetry elements for tetrahedra? Does it have a C3? Tetrahedra has a C3. Does it have a C3? No. So if you look at any molecule, this molecule, the way I'm going to look at is if you were to look at this molecule like this, right? I'm trying to hold it from the thing here. Right? So that is this molecule. So if you were to now draw a line going through this, look at my finger here, that's your C2 there, because that brings this here, that there, this bottom one in the front and the front one to the bottom. So that's a C2, and you have 2 reflection planes, one that contains carbon and 2 hydrogens, and the other one contains carbon and the 2 chlorines. So we have 2 reflection planes, 1 C2. So that makes it the C2V as the point group for CH2Cl2. Am I making sense here? For some of you who took my class, you knew this, but I'm repeating it again for the sake of those who did not take my class before. But this is how you derive at this point group classification. It has 1 C2 and 2 reflection planes. All right. So that's a C2V. So if you now look at C2V here in the bottom of the screen, C2V has, remember we talked about this as an identity, a C2 and 2 reflection planes. All right. Now, what I'm going to ask you to visualize is what happens to these bonds when each of these operations are carried out. Do they move or don't they move? Okay. A total of 4 bonds are there in this molecule, right? There are 2 CH bonds and 2 CCl bonds. Okay. Now, if you do nothing, how many bonds remain in place? I have 4 bonds. I have 4 bonds. If I do nothing, all the bonds will stay where they are, right? So there is absolutely no change in any of the 4 bonds. So the value of E here is given as 4 because all 4 remain in place. Remember, we told you that doing nothing is also a symmetry operation. Now coming to the C2. If you now look at this molecule, the C2 is in between the angle of Cl, CCl, right?
bisecting the angle between HCH also. That's your C2. When you rotate the molecule along C2, all 4 bonds move. For that reason, the value for C2 is given as 0. Now, for coming to the reflection planes, if you use this reflection plane, that is carbon and 2 chlorines, that is the plane that reflects the 2 hydrogens back and forth, right? So if we now look at that, 2 bonds stay and 2 bonds change. So we say the sigma V is 2 here. Similarly, if we were to now turn around and use C2, there's carbon and 2 hydrogens now, that's the plane. And when you do a reflection, the chlorines will change. So we say 2 CCl bonds are moving, but 2 CH bonds are in place. So 2 are not moving, 2 are moving. So we only put the number that does not move. So we have 4022. This is your reducible representation. Okay, the tau sigma. Why did we put sigma? Because this molecule has only sigma bonds, no pi bonds, no double bonds, right? So we say these are all sigma bonds, and there are 4 of them. All of them move under C2, but 2 remain in place in both of the vertical planes of symmetry. Okay, so given any molecule, you should be able to write what we call reducible representations. Am I making sense here? Suppose if I were to change this to, I'm just changing it to look like water. You have oxygen in the middle, 2 hydrogens. Okay, that's the shape of water molecule. Now, tell me what would be the E value here? Any guess?
2.
It will be 2 because I have only 2 bonds. And what will be the value for C2? C2 is that's my finger, right? That's your C2 because when you rotate this molecule by 180, it comes back to normal shape, original shape. So that's your C2. So when I'm rotating this, did you see any bonds staying in place?
No.
2 bonds, right? Both of them moving. The C2 value will be 0. And if I'm reflecting in the plane that is bisecting this oxygen atom here, and we have 2 hydrogens on either side of the plane, when you do the reflection, what happens now to the bonds? That should be 0, right? Because you are now moving both the bonds. And because water is a planar molecule, it has again a plane of symmetry. So if you want to reflect water molecule in the same plane where the atoms are located, the bonds stay in place. So one sigma will have 2, the other sigma will have 0. So the irreducible representation of water is going to be 2020, 2020 in the C2V point group. So you should be able to look at different molecules. Suppose if I were to have planar molecule BCl3, or I'm sorry, BFCl2. If you can see this picture here, boron in the middle, planar molecule. I have chlorine, the blue one, and fluorines, the red ones. So this is BF2Cl. What should be the point group for this?
C3.
Hmm?
C3.
No?
Oh, sorry, C2, my bad.
C2?
Yes, C2.
C2V. Is that what you mean? It's supposed to be C2V.
Yes.
Okay. So although water, CH2Cl2, and BF2Cl, they all have C2, but the reducible representation is different, right? So what should be the character for E for this molecule? How many bonds do you see? You have 1, 2, 3 bonds, right? BF2Cl. So your E value will be 3. Am I making sense at all? Okay. Similarly, if you're doing C2, in this case, C2 will be 1. One of the, because you're rotating along the BCl bond, so that bond stays in place. So the C2 value becomes 1. So the character values that you see for reducible representation for even the same point group will be different depending on the actual geometry of the molecule. CH2Cl2 will have an E value of 4, water will have an E value of 2, and BF2Cl will have an E value of 3. Am I making sense here, folks? Okay. So in the next lecture, we will continue from here. It's already 3:15, 3:12, because I need to now explain to you how a reducible representation that we just got for CH2Cl2, the tau sigma is 4022. Now, how that should be tied up to the periodic or the character table in terms of defining the irreducible representations. All right, we will do that Tuesday. Questions so far? So this is a part 1 of the lecture, and the part 2, we are going to do this and some more examples of, symmetry adaptive linear combination of orbitals using the character tables. As you can see, this is all descriptive chemistry. We're not using, technically speaking, if the same topic were to be taught in a PChem, you'll be doing a lot of linear algebra, where it's using matrices and trying to multiply the matrices and then, normalizing the matrices and all that stuff. We are not doing all that. We are giving you purely a descriptive chemistry. But still, it teaches you the same, the answers are still the same. Whether you use matrices and spend 5 hours solving the problem, or just do 3 minutes of this calculation, the results are still the same. Okay. So stay safe, and we will see you in the next lecture.